If we'd like to make use of our three-dimensional structures and of our individual bond dipoles, we want to find out net dipoles, because long-term that's what's going to determine our intermolecular forces for us. And when we had mentioned dipoles in a previous video, we discussed this idea that we can use deltas or we can use arrows to show individual dipoles. And the arrows were actually vectors, right? Things that have magnitude and direction. So what I'm going to do here very quickly, just run through adding some vectors visually and then adding them in terms of compounds in 2 dimensions, and then maybe just mention how it works for 3 dimensions. Let's take a look at just the idea of resultants and things like that. In math class, you may have used vectors graphically for sines and cosines and horizontal and vertical components of things. In physics class, similarly, you might talk about velocity versus speed, where velocities give you a direction and a magnitude, so that's a vector, versus speed, which is just a scalar quantity. Now, what we are really doing, and I think the easiest way to handle this, and we're taking all the math out, but there's lots of great math involved, is we're going to treat them like directions on a treasure map. And I know it sounds lame, but it works out pretty well for us. Our goal when we're doing this, there's like additive properties and things like that. The order you add them doesn't matter. So we're going to add the vectors tip to tail, right? And then at the end, you're going to draw a line from where you started to where you ended up. What we're going to do is make up some instructions for our treasure map and follow them through and see what our net displacement of is in a situation like this. So we'll just say, for instance, we'll go like 10 paces to the right, then 3 up, and then 2 left, and 3 up, and maybe 1 to the right. All right, whatever that is. X marks the spot, right? So if we are starting maybe right here on our map, I want to go 10 paces to the right, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So I would have a vector this large in this direction. And then my next step is to go 3 up. And so I will start here. You don't go back to the beginning. If you're on your hunt for your treasure, you're going to pick up right off after the last instruction. And we're going to go 1, 2, 3 up. And now I'm supposed to go 2 steps to the left. So I'm going to go 2 steps to the left. Then I need to go 3 steps up again. 1, 2, 3. And then I need to go 1 step to the right. All right. Now, you'll notice that as we went, I added those tip to tail, tip to tail, tip to tail. And then in the end, I'm going to connect them from where I started to where I ended up. In this particular case, our resultant from where we started to where we ended up. And I did not draw the best arrow here to represent that that's where we ended up, but there's that point. Okay. I would like to point out that the treasure map style instructions weren't technically necessary. If someone could have just given you like an angle and a direction, you could have followed 1 step. But that's not how treasure maps are usually written, if indeed they ever existed. So we're going to use this same strategy for mapping out net dipoles on chemical compounds using their 3-dimensional structures. And the easiest way to start is going to be for us to look at 2-dimensional structures.